Advanced control theory first module കുറച്ച് topics ആണ് ഞാൻ ഇന്നത്തെ വീഡിയോയിൽ കവർ ചെയ്യാൻ പോകുന്നത്. ഓക്കേ, ഇതിൽ ഫസ്റ്റ് മോഡ്യൂളിൽ ബേസിക് ആയിട്ട് പറയുന്ന കാര്യങ്ങൾ കൺട്രോളേഴ്സ് ആൻഡ് കോമ്പൻസേറ്റേഴ്സ് ആണ്. നമുക്ക് ഈ വീഡിയോയിൽ കോമ്പൻസേറ്റേഴ്സ് എന്താണെന്ന് നോക്കാം. Compensator is a device inserted into the system for satisfying the specifications. ഇവിടെ സ്പെസിഫിക്കേഷൻസ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ എന്തൊക്കെയാണെന്ന് നിങ്ങൾക്ക് അറിയാം ഓൾറെഡി. ടൈം ഡൊമൈൻ സ്പെസിഫിക്കേഷൻസ് ഉണ്ട്, ഫ്രീക്വൻസി ഡൊമൈൻ സ്പെസിഫിക്കേഷൻസ് ഉണ്ട്. റൈസ് ടൈം, പീക്ക് ഓവർഷൂട്ട് എക്സെട്ര comes under time domain specification. Similarly, settling time also comes under time domain specification. But phase margin, gain margin, bandwidth etc. comes under frequency domain specifications. Then compensator introduces pole and zero in open loop transfer function to modify the performance of the system. Compensators may be series compensators and parallel compensators or feedback compensators. In module 1 and 2 we are dealing with the series compensation. G of S is the original process or forward transfer block. To improve the specifications or to improve the performance of the system, we are designing compensators and it is adding in series with the series with the process or original system. See the figure 1.1. To choose whether series or parallel compensation is required for our system, we are considering the following factors: the nature of signal in the system, then power levels at various points, then components available, then designer's experiences or economic considerations. Compensators may be many types: pneumatic type, mechanical type, electrical or electronic compensators are available in market. And we are dealing with electrical or electronic compensators, and the types of electrical or electronic compensators are lag compensator, lead compensator and lag lead compensator. Normally the system with type number 2 and above are less stable, and for such system lead compensation is required because the lead compensator increases the margin of stability. But the system with the type 1 or 0, we are using any of the three compensators, that is lag, lead or lag lead. And these compensators may be designed using two approaches, that is root locus approach and frequency domain approach. In frequency response approach we are using Bode plot, Nyquist plot, Nichols plot etc. The root locus approach is a time domain approach, and the advantage in this design is that information about the closed loop transient response and frequency responses are directly obtained from the pole 0 configuration of the system in the S-plane. The design information about the transient response and frequency response are directly obtained from the pole 0 plot. But in frequency response approach, it is not depends upon time, it depends upon the frequency, and the effects of disturbances, sensor noise and plant uncertainties are relatively easy to visualize and assess, and it is an easy method for using experimental information for design purpose. But the disadvantage of frequency response is that the design information about closed loop transient response and frequency responses are indirectly obtained from the pole 0 configuration. Not obtained directly, the responses are indirectly obtained from the pole 0 configuration of the system in the S-plane. Now let's move on to lag compensator. The special features of lag compensators are: it is a compensator having the characteristics of a lag network. By implementing lag compensator, large improvements in steady state performance are achieved. large improvements in steady state performance but not in transient performance. The lag compensator reduces the bandwidth of the system and will result in slower transient response. Then essentially a low pass filter the lag compensator is essentially a low pass filter and high frequency noise signals are. Now let us see the explained representation of a lag compensator. Normally a compensator means we are adding poles and zeros to the system. So a compensator transfer function GC of S can be represented as S plus ZC divided by S plus PC. That is, we are adding a zero and we are adding a pole. Every compensator will have the transfer function like this. GC of S plus ZC divided by S plus PC, where ZC is called the zero of the compensator and PC is called the pole of the compensator. For a lag compensator, we are writing this in the form S plus 1 by T divided by S plus 1 by beta T. So 0 ZC equal to 1 by T and PC equal to 1 by beta T. So 0 at minus 1 by T and pole at minus 1 by beta T. By looking this figure, we know that for a lag compensator, always pole is near to origin. ഒറിജിനോട് അടുത്ത് എപ്പോഴും പോളായിരിക്കും, ഒറിജിനിൽ നിന്ന് അകലെയായിരിക്കും, പോളിനേക്കാളും അകലെയായിരിക്കും സീറോ ഉണ്ടാവുക. For this to happen, always beta should be greater than 1. So for a lag compensator, GC of S equal to S plus 1 by T divided by S plus 1 by beta T, where T greater than 0 and beta greater than. Once more, the zero of lag compensator ZC equal to 1 by T, pole of lag compensator PC equal to 1 by beta T. So 1 by T can be substituted as ZC, that is ZC by beta, and from this equation we get T equal to 1 by ZC and beta equal to ZC by PC. Next, let us see the practical realization of a lag compensator. See this electrical network. This electrical network has 3 elements, 2 resistors and 1 capacitor. And this network is represented in S domain, so capacitor is written as 1 by SC. And we are applying input voltage EI to the system, and we are taking output from resistor and capacitor, across resistor and capacitor. So the transfer function of this network is Laplace of output by Laplace of input at the zero initial condition, that is E0 of S divided by EI of S. Okay. Using voltage division rule, we are writing E0 of S, that is output voltage across this element, this branch, is equal to total voltage applied EI of S into resistance of that branch and impedance of that branch, that is R2 plus 1 by SC, divided by sum of the resistances, that is R2 plus 1 by SC plus R1. See. Now rearranging this equation, we will get like this: EI of S into SC R2 plus 1 divided by SC into R1 plus R2 plus 1. And the transfer function E0 of S by EI of S is taken, and we are rearranging this transfer function in such a way that it is similar to lag compensator transfer function. What is lag compensator transfer function? That is S plus ZC divided by S plus PC. Now see this equation, E0 by EI. This is S plus a constant divided by S plus another constant. So this S plus 1 by T and this is S plus 1 by beta T. So what is 1 by T? 1 by T equal to 1 by R2C. Similarly 1 by beta T. Where T equal to R2C and beta equal to R1 plus R2 divided by R2. That is, we are combining this equation with the general equation of the lag compensator transfer function S plus Hc, that is S plus 1 by t divided by S plus 1 by beta t. And we are getting t equal to R2C and beta equal to R1 plus R2 by R2. Then let's move on to frequency response of lag compensator. We already said that Gc of S equal to S plus 1 by t divided by S plus 1 by beta t. That is the compensator. Now rearranging, taking xt plus 1 divided by 2 and t and t get cancelled. Then beta comes outside. Then we are substituting S equal to j omega, Gc of j omega c. Okay. Then here we are having a constant called beta. We can say that a lag compensator provides a DC gain of beta. And if the DC gain of the compensator is not desirable, then it can be eliminated by a suitable attenuation. Let us assume that the gain beta is eliminated by a suitable attenuation network. That is, removing beta is not very difficult. Just implement a scaling plot. So we are dealing with the rest of the function, rest of the transfer function, that is 1 plus j omega t divided by 1 plus j omega beta t. So Gc of j omega equal to 1 plus j omega t divided by 1 plus j omega beta t. This is in A plus jb form. The magnitude equal to root of a square plus b square, angle tan inverse b by a. Similarly in the denominator also. So both this magnitude results the resultant magnitude, similarly angle. So the magnitude equal to, so the magnitude is equal to root of 1 plus omega t square divided by root of 1 plus omega beta t square, and angle tan inverse omega t minus tan inverse omega beta t. When this angle comes to upside, it becomes minus. Okay. Now we are plotting the frequency response. Frequency response means magnitude versus frequency, that is magnitude response, and phase versus frequency is the phase response. I am saying once more. Frequency response has two parts, magnitude response and phase response. Magnitude versus frequency will give magnitude response. Phase versus frequency will give phase response. So to draw the frequency responses, we are considering the corner frequencies. Here corner frequencies are omega c1 and omega c2 are. Then if it is in 1 plus st form, the corner frequency is 1 by t. And 1 plus st, if here the corner frequency is 1 by beta t. We know that beta is greater than 1. So 1 by beta t is less than 1 by t. So we are taking 1 by beta t as omega c1, that is lower cutoff frequency, and omega c2 as 1 by t as the upper cutoff frequency. To draw the frequency plot, that is to draw the magnitude plot or phase plot, we are taking these corner frequencies omega c1 and omega c2 and the frequencies which is less than omega c1 and frequencies which is greater than omega c2. In these four frequencies we are calculating the magnitude and we are drawing the plot. Since beta t greater than 1, omega c1 less than omega c2, we know that. And we are taking the magnitude in decibel. We are 20 log of magnitude will be the magnitude in decibel. At very low frequencies, that is frequencies less than omega c1, omega t less than 1 and omega beta t very less than 1. So A equal to 20 log 1. These two terms will get cancelled and root 1 by root 1 equal to 1, 20 log 1 equal to 0. In the frequency range omega C1 to omega C2, omega t less than 1, omega beta t greater than 1. So we will get A equal to 20 log 1 by root omega beta t square. So 20 log 1 by omega beta t. So in this range, from the up to omega C1 means for every frequency is less than omega C1, the magnitude is 0, a constant magnitude. But from omega C1 to omega C2, the magnitude A equal to 20 log 1 by omega beta t. So the magnitude A depends upon omega. For each omega, the magnitude changes. Now see, at very high frequencies, after omega C2, omega t very greater than 1 and omega beta t also greater than 1. So 1 can be neglected. So A equal to 20 log like this, that is 20 log 1 by beta. Here beta is constant, not a varying quantity. So again A equal to 20 log 1 by beta as a constant term. So from omega C2 to all other higher frequencies, the magnitude will not changes. Now see the diagram. This is the magnitude plot. Up to omega C1, the magnitude is 0. Then from omega C2 to higher frequencies, the magnitude is a constant and that constant value is 20 log 1 by beta. Then omega C1 to omega C2, it changes. See, and it changes with the equation, changes to 20 log 1 by omega beta t. Okay. Similarly, the phi equation. Phi equation is tan inverse omega t minus tan inverse omega beta t. At omega equal to 0, this phi equal to 0. At omega equal to infinity, tan inverse infinity 90 minus 90, this is again 0. So the phase plot for lower frequencies, magnitude of the phase is 0. At higher frequencies also phase is 0. But between these frequencies, the phase changes like this, and at a particular frequency this phase will become maximum, and the frequency corresponding to this maximum phase is called omega m. We can say that the first corner frequency 1 by beta t omega c1, and the upper cutoff frequency or upper corner frequency 1 by t omega c2, and the omega m is equal to 1 by t root beta, that is omega m equal to root of omega c1 into omega c2 equal to 1 by t root beta. So this is the frequency response, that is magnitude response and phase response of the Lager compensator. Okay, now the omega m value 1 by t root beta can be derived by formula. Okay, let us see how to determine omega m and phi m. To get the maximum value of any quantity, we have to differentiate the equation and differentiate with respect to the variable parameter and equal to 0 and find the values. So the phi equation, we know that phi equation tan inverse omega t minus tan inverse omega beta t. See the previous page. Differentiating, differential of tan inverse equal to 1 by 1 plus beta square. So we will get 1 by 1 plus omega t square into t. Then minus etc. Okay. And substitute. When the differential equal to 0, we know omega will have the maximum value. So we are substituting omega equal to omega m. Now rearranging these equations, we will get omega m is equal to 1 by t root beta. So the frequency corresponding to maximum phase equal to 1 by t root beta. Now to get the phi m, we are substituting this value of the frequency in the phi equation, that is tan phi equal to phi is equal to tan inverse omega t minus tan inverse omega beta t. We are applying tan on both sides, then rearranging and substituting omega equal to omega m. We will get tan phi m is equal to 1 minus beta by 2 root beta, or phi m is equal to tan inverse 1 minus beta by 2 root beta. This equation and omega m is equal to 1 by t root beta both are very important and the same procedure. Now to get beta from this equation, we are taking a triangle. We know phi m is equal to tan, that is tan phi m is equal to 1 minus beta by 2 root beta. We are marking this angle as phi m, then tan phi m is equal to opposite by adjacent, opposite equal to 1 minus beta, adjacent equal to 2 root beta. Then hypotenuse of the triangle is equal to root of adjacent opposite square plus adjacent square. By calculating, we will get it as 1 plus beta. So sin phi m, sin theta equal to opposite by hypotenuse, sin theta into 1 plus beta equal to 1 minus beta, and rearranging, we will get beta equal to 1 minus sin phi m by 1 plus sin phi m. So here phi m is the maximum phase change required, and we are designing a compensator to give this maximum phase difference. We will select beta according to this equation. Okay.